Okay, good afternoon, everyone, and welcome to the most recent webinar event of the 2DCC. Today we have Dr. Choi-Zoo Cheng. He's from the Department of Physics at Penn State University. He's also one of the faculty members on the 2DCC grant. So welcome to Dr. Cheng.
Yeah. Thanks everyone for coming. And my name is Choi-Zoo Cheng. I joined Penn State 2 years ago, and I'm very happy to give this talk today here. And the title of my talk is Quantum Anomalous Hall Effect in the Magnetic Topological Insulator Thin Field. And this is the outline of my talk. At first, I will give a brief introduction about the quantum anomalous Hall effect and topological insulator. I will show you why and how we use the topological insulator to realize the quantum anomalous Hall effect. With many efforts, I was very lucky to become the first one to realize the quantum anomalous Hall effect in chromium and vanadium doped system, both for the first time. And in 2017, I joined the Penn State, and at Penn State, I fabricated the quantum anomalous Hall semi-structure. In this kind of semi-structure, we observed the axion insulator state and the crossover of the quantum anomalous Hall effect between the topological Hall effect and the quantum anomalous Hall effect. And finally, I will give a brief summary. Let's start with the Hall effect. We all know the Hall effect, and Hall effect means when a current flows through a conductive material, which is in a perpendicular magnetic field, transverse voltage will be formed. And the carrier will be pushed toward to the side of this material, and a transverse voltage will be formed. This voltage usually called Hall voltage, and this effect called the Hall effect. The Hall effect was first discovered in the 1879 by Adam Hall. At that time, Adam Hall is a graduate student at Johns Hopkins. And this is the Adam Hall's original data on the good leaf. And you know now is the Hall effect is widely used to identify the carrier density and carrier mobility in the conductive material. And about 100 years later, in the 1980s, the quantized version of Hall effect called quantum Hall effect was discovered by von Klinze in Germany. This is the quantum Hall effect in the 2D electron gas, and we see that the Hall resistance is quantized at the same time the longitudinal resistance goes to 0, and the quantum Hall effect is usually observed in the at the very low temperature and very high magnetic field in the 2D electron gas. And we know that the quantum Hall effect is usually observed at very high temperature. We will naturally ask one question: can we realize the quantum Hall effect without the need of magnetic field? This kind of quantum Hall effect is called quantum anomalous Hall effect. And before we introduce the quantum anomalous Hall effect, let me introduce the Hall family. There are 3 basic members: Hall effect, anomalous Hall effect, and spin Hall effect, and their quantized version called quantum Hall effect, quantum anomalous Hall effect, and quantum spin Hall effect. So today in my talk, I will focus on the realization of the general belief, the last member of Hall family, called quantum anomalous Hall effect in the magnetically built topological insulator thin field. In the quantum anomalous Hall effect at 0 magnetic field, the eddy state depends on the magnetization of the sample. When the magnetization up, the edge goes this way. When the magnetization down, the edge goes the opposite way. So the chirality of the eddy current in the quantum anomalous Hall effect depends on the magnetization of the sample. And in the quantum anomalous Hall effect at 0 magnetic field, the Hall resistance is quantized. At the same time, the longitudinal resistance is 0. So there is ballistic eddy transport in the quantum anomalous Hall effect. And unlike the quantum Hall effect, you know the quantum Hall effect was first observed in the experiment, and later there are lots of theories to try to explain. Actually, the quantum anomalous Hall effect was first predicted by Duncan Haldane in 1988. You know, the Duncan Haldane got the Nobel Prize just because of his great contribution to the first prediction of the quantum anomalous Hall effect. And in Haldane's model, it's based on one layer carbon lattice, now usually called graphene, in a periodic magnetic field, but without lattice. And Haldane takes the nearest neighbor Hawking and the second nearest neighbor Hawking in his calculation. If the second nearest neighbor Hawking is 0, that's just there is Dirac cone at the corner of the Brillouin zone. This is just the graphene and the band structure of graphene. If we consider the phase of the second nearest neighbor Hawking, so the time reversal symmetry of this system will be broken and a gap will open at the Dirac point. So if Haldane predicted, if we tune the chemical potential into this gap, we in principle we can realize the quantum Hall effect at their magnetic field. At that time, there is no quantum anomalous Hall effect definition. So, but we know that in the graphene, the spin orbit coupling is very weak, so it's almost impossible to realize quantum anomalous Hall effect in the graphene-based system. So in the next after the 1988, in the following 20 years, there is very little experimental progress in this direction, and the quantum anomalous Hall effect can be also considered as the quantized version of anomalous Hall effect. We know anomalous Hall effect is very common in the ferromagnetic material, and if we can quantize the anomalous Hall effect, we can also realize the quantum anomalous Hall effect. About the mechanism of the anomalous Hall effect, somebody thought that the anomalous Hall effect is just an extrinsic property is induced by the impurity in the material. And in the 1954, Kempler and Latinger first time thought the anomalous Hall effect was induced by the property of the energy band. It is an intrinsic property of the material. And the Hall conductance can be calculated by the integral of the Berry curvature. The Berry curvature is determined by the chain number. So we can get the Hall conductance is just E squared over H times the chain number. So if from this equation, we can say if we want to realize the quantized anomalous Hall effect, we need non-zero C, and this material should be a ferromagnetic material. There should be anomalous Hall effect in this material. The non-zero C just means there is inverted band in this material. This now we usually call this material topological material. And in 2006, the discovery of topological insulator makes the realization of the quantum anomalous Hall effect become possible. We know that in topological insulator, the conduction band and the valence band has been inversed. Obviously, it satisfies the first condition of the quantum anomalous Hall effect. So let me say a few words about the topological insulator. This is a binding insulator. This is a conduction band. This is valence band. If we introduce very strong spin orbit coupling into a binding insulator, the conduction band and the valence band will be reversed, and linear dispersion surface state will be formed. This we call the Dirac surface state. This material we call topological insulator. So the topological insulator can be classified in 2D topological insulator and 3D topological insulator. And both 2D topological insulator and 3D topological insulator has been realized in the realistic material. The first 2D topological material was first discovered in the microtoroid quantum wells, and later in the indium arsenide and gallium antimony quantum wells, and most recently the quantum spin, the 2D topological insulator, also called quantum spin Hall effect, was discovered in the monolayer constant toroid field. And the 3D topological insulator was first discovered in the bismuth antimony compound, and later in this kind of bismuth selenide family material. So my experiment mainly based on this material, because in this material, the band structure is very simple, and there is only one Dirac point, and the gap is big, is almost 300 millieV. And let me see how we can realize the quantum anomalous Hall effect in the topological insulator. This is a topological insulator. This is the Dirac surface state. It is protected by the time reversal symmetry. If we introduce the ferromagnetic order in topological insulator, the time reversal symmetry is broken, and a gap will be open at the Dirac point. This is not the bulk. This is the bulk gap. This is a gap within the bulk gap. This gap usually very small. The theories predicted if we can tune the chemical potential exactly located in this magnetic exchange gap, in principle, we will realize the quantum anomalous Hall effect. This is just a theoretical picture how to realize quantum anomalous Hall effect in the magnetic topological insulator. Let's transfer to the experimental step. In the experiment, if we want to realize the quantum anomalous Hall effect, there are 3 steps. The first step is we need very thin film or topological insulator. So our approach is MBE growth. And the second, we need to introduce the ferromagnetic order into topological insulator thin film to break the time reversal symmetry. Our approach is magnetic doping. The third step is we need to carefully tune the chemical potential into the magnetization gap. This is also the most challenging gap. In our experiment, we take these 2 ways. One is chemical doping, the other is gating effect. So next, I will show you how to realize quantum anomalous Hall effect in the experiment, step by step. So the first step is how can we get the thin film of topological insulator? Our approach is MBE. So we use MBE to grow the 3D topological insulator bismuth cyanide family material. This is the bismuth cyanide film growing on the graphene substrate. So this is the RPES data. We can see we can get the 1 quintuple layer to 6 quintuple layer. Quintuple layer means the 5 layer in the topological material. Usually 1 quintuple layer just 1 nanometer. So we can see that when the thickness is 6 quintuple layer, there is Dirac cone. When the thickness below 6 quintuple layer, there is a gap opening, especially between 3 quintuple layer and 5 quintuple layer. We can see the Rashba splitting. This Rashba splitting just induced by the top surface state and the bottom surface state hybridization. So besides RPES, we also use the STM to check the quality of the film. We use STM and RPES as the group's eye to characterize the film quality. So this is the large scale of the STM image. We can see the terrace is atomically flat, and this is the atomic resolution STM image. We can see that we can clearly distinguish the selenium atom on top of the bismuth cyanide. And in this typical site, there is no any defects. So that also confirms the quality of the MBE group film is very high. And we use MBE to get the thin film or topological insulator. The second step, how can we introduce the ferromagnetic order in the topological insulator? So the very straightforward way is we just deposit the magnetic material on top of this topological insulator. So the conventional magnetic material, usually iron, cobalt, nickel, they are very reactive and they have very high surface energy. But for the bismuth cyanide family material, they are selenium and tellurium based and with low surface energy. So when you deposit the iron, nickel, or cobalt on top of the topological material, they will react to each other and makes the interface not very good. So in our experiment, we take the method in the diluted magnetic semiconductor field. We doped some transition metal in the sample, get this ferromagnetism in the topological insulator. So we know there are 3 basic members in the bismuth cyanide material: bismuth cyanide, bismuth telluride, and antimatter telluride. So we doped some chromium in this kind of, we tried all the transition metal and finally find chromium is better, so it's best. So we can see in chromium doped bismuth cyanide, there is just a nonlinear behavior. This is just paramagnetic property, so it's not very good for the quantum anomalous Hall effect. We forget this material. So for the chromium doped bismuth telluride and antimer telluride, we can see this one, the anomalous Hall effect is much more squared. So this one, the ferromagnetic order is better. So we choose from the transport data, the chromium doped antimer telluride is the best material for the realization of the quantum anomalous Hall effect. So we choose this material as the parent material for realizing the quantum anomalous Hall effect. Let's take a careful look about the transport data of chromium doped antimer telluride. In this material, this is quintuple chromium doped antimer telluride. This is the temperature dependent Hall traces. We can see at the low temperature, it shows very square anomalous Hall hysteresis. And this Hall resistance is almost 80 ohm. It's much lower than the quantized value. We know the quantized value is H over E squared is about 25.8 kilo ohm. And the reason is because in chromium doped antimer telluride, the periodicity is too high. It's 10 to 14. Indicates the chemical potential is crossing the bulk valence band. So so until now we realize we have achieved the thin film of topological insulator. We also demonstrated the ferromagnetic state in this kind of magnetic doped topological insulator. The third step is how to reduce the periodicity, how to tune the chemical potential into the magnetic exchange gap. So we use these two methods, chemical doping and gating effect. Let's check the first way. So this is the band structure of the bismuth telluride. This is the conduction band, this is valence band. So in bismuth telluride, the chemical potential usually crosses the conduction band. So the carrier in bismuth telluride is N-type. So this is the band structure of antimer telluride. The chemical potential usually crosses the bulk valence band. So the carrier is P-type. So in order to get the intrinsic topological insulator, we mix the bismuth telluride and antimer telluride. It is possible to make the chemical potential cross the Dirac point. So it is possible to tune the chemical potential approaching to the charge neutral point. Let's see this chromium. Let's see chromium doped bismuth antimer telluride. This is the upper band of the 5 quintuple layer chromium doped bismuth antimer telluride. This is the band structure of antimer telluride. It's P doped. The Dirac point is above the chemical potential. When we doped some chromium inside, it's a little bit Hall doped. And if we introduce some bismuth, the Dirac point is approaching to the chemical potential. In the 40% dope, the Dirac point is below the chemical potential. So around x equals 0.25, the chemical potential is crossing the Dirac point. The reason we didn't see the magnetic exchange gap because the measurement temperature is 150 Kelvin. So at this temperature, there is no ferromagnetic order. So let's check. We want to detect the quantum anomalous Hall effect. So we need to use transport to measure the quantum anomalous Hall effect. Let's check the transport result of 5 quintuple layer chromium doped bismuth antimony telluride with the different bismuth antimony ratio. This is the this is chromium doped antimony telluride. This is 15% bismuth doping, 20%, 25% to the 50% bismuth doping. We can see when we tune the X, when we tune the bismuth doping, the ferromagnetism always there. So the ferromagnetism can survive in P-doped and N-doped chromium doped bismuth antimer telluride. This is a very good news. You know, in the diluted magnetic semiconductor, the ferromagnetism is usually achieved in the P-doped sample. When you tune the sample to the insulating regime or to the electron doped regime, the the ferromagnetism will disappear. So but in this material, we can see that in p-doped regime and n-doped regime, all the ferromagnetism always there. And we can see the anomalous Hall resistance in this kind of between the p regime and p-type and n-doped, a little bit bigger than this way. And we can see there is a crossover between the n-doped and p-doped between the 0.2 and 0.25. Let's summarize the anomalous Hall resistance and the longitudinal resistance at zero magnetic field as a function of the bismuth content. We can see that the anomalous Hall resistance indeed shows a peak when the sample in the insulating regime, and the longitudinal resistance also shows a peak in this regime. And if we plot the ratio between the anomalous Hall resistance and longitudinal resistance, we usually also call this anomalous Hall angle as a function of bismuth content. We can see this also shows a peak in the insulating regime, and in the very high electron doped regime, p-doped Hall doped regime, the Hall angle is 0.01, is similar as the conventional magnetic material. And in this kind of insulating regime, the Hall angle is almost 0.15. So it tells us when you make the sample become insulating, when you tune the chemical potential, approaching to the magnetic exchange gap, the Hall resistance indeed become bigger. So the reason we can realize this kind of phenomena in the magnetic doped TI, because the ferromagnetism in this kind of magnetic doped TI is induced by the fan flag, not as the conventional diluted magnetic semiconductor. It's usually induced by the RKKY. It's related, depends on the carrier density of the sample. So the second step is we use the gating effect. We know that using the chemical doping is very difficult to finely tune the chemical potential to the magnetic exchange gap. So we introduce the gating effect. You know, in this 5 quintupole layer chromium doped bismuth antimony telluride, we can see when we tune the gate, the anomalous Hall resistance is changed, and but the HC almost the same. That means the ferromagnetic order has very little change when you tune the carrier density of the sample, but the anomalous Hall resistance is almost has 1 order change. In this sample, we can see at the 250 millikelvin at 35 volts, the Hall resistance is about 6.5 kilo. It's almost a quarter of the quantized value. It's still far from the quantized value. So in the next, that's the first year's work, and in the next following years, I grew almost 2,000 samples and systematically changed the chromium doping, also changed the bismuth antimony ratio to tune the periodicity of the sample, and we changed the thickness of the sample. Also, you know that the MB growing sample, if you take the ICQ transport measurement, it's very sensitive. You need to put some protection layer. So we also tried a different protection layer and make the try different configuration of the whole bar device. And we're using this loop to improve the Goose parameter for the magnetic doped TI. And finally, in the 2012, in October 9th, and we are the first to see in this sample, we are the first to see the quantum anomalous Hall state. You see, this is the 1.5 Kelvin data. In this sample, the Hall resistance is almost 17 kilo ohm, and the longitudinal resistance is also almost 16 to 17 kilo ohm. The Hall angle is almost 1. The reason we decide there is quantum anomalous Hall state in this sample is because this. So if we plot the zero field longitudinal resistance and Hall resistance as a function of the gate voltage, we can see in this sample, different from the previous sample. In this sample, we can see the Hall resistance goes up. At the same time, the longitudinal resistance goes down. So we know that in the ferromagnetic material, the Hall resistance is usually proportional to the longitudinal resistance. But in this sample, the the Hall resistance become bigger, this becomes smaller, indicates there is some quantum state, there is some ID state in this sample. So this measurement at 1.5 Kelvin, so we try the dilution temperature measurement, and finally in this quantum, in this 5 quintuple layer quantum chromium doped bismuth antimaterial sample, we are the first to achieve very nice quantum non-spore state. This is at the charge neutral point. We can see this is the magnetic field dependence of Hall longitudinal resistance and Hall resistance. We can see at 30 millikelvin, the Hall resistance is quantized and the longitudinal resistance is approaching to 0. If we plot the zero magnetic field, Hall resistance and longitudinal resistance as a function of gate voltage, we can see the Hall resistance is quantized here. There is a plateau. At the same time, the longitudinal resistance goes to shows a sharp dip. So this phenomenon marks the observation of the quantum non-spore effect. And our work is also was featured in the scientific background of the 2016 Nobel Physics Prize to demonstrate the great contribution of Duncan Haldane. So, but we need to say, we know that in this sample, at zero magnetic field, the Hall resistance is quantized, but the longitudinal resistance is not zero. So at zero magnetic field, the chiral transport in this quantum non-spore sample is not completely dispenseless. So let's see the high magnetic field data. So this is the Hall traces and the longitudinal longitudinal resistance at a high magnetic field. We can say the Hall resistance is quantized at high magnetic field. The Hall resistance is quantized and the longitudinal resistance exactly goes to 0. So means that at high magnetic field helps the localization of the dispensing channel in the sample. So we can achieve the dispenseless chiral ID transport in this sample at high magnetic field. So in 2013, I moved to the MIT. I'm thinking to realize a better system to enhance the observing temperature of the quantum non-spore effect. And I found that in this vanadium doped bismuth telluride sample, the theory, there is some theory predicted the quantum non-spore effect in the magnetic doped GI. Theory said there is no quantum non-spore effect in vanadium doped GI. But I found in this vanadium doped GI, the ferromagnetism is much better. With the same doping, the TC is higher and the HC is about 10 times of the TC in the chromium doped sample. We can see in this 4 quintuple layer vanadium doped bismuth antimaterial, we can see the Hall resistance quantized. At 0 field, the longitudinal resistance is just 3 ohm. So the Hall angle is very close to the 90 degree. And this kind of very high precision quantum non-spore effect is further confirmed by the temperature dependence of longitudinal resistance, Hall resistance, and Hall angle. So we can see for the temperature dependence longitudinal resistance, it shows a continuous dip below the 5 Kelvin. So in this sample, the quantum non-spore effect can survive up to 5 Kelvin. So after our work, so we are the first to realize the quantum non-spore effect in chromium doped system and vanadium doped system, both for the first time. So after our work, there are several groups all over the world. We produced our work. This is the this is Conwang's group work at UCLA for the chromium doped system. And this is the work from the Topological group in the Tokyo and Riken, and this Nitin's group at Penn State. So for the vanadium doped quantum non-spore effect is also reproduced by the Lawrence Mollenkemp's group at Würzburg in Germany, and also reproduced by my previous supervisor, Qikun Xue's group at Tsinghua University. So in 2016, I moved here and built my own lab. The first project with calibrated with Nitin, Moses, and Toshing. The first project is how to realize the axion insulator state in this kind of magnetic TS sample. So this is the axion term in the topological insulator. Just because of this E dot B term in the topological insulator, there are a lot of interesting phenomena in this kind of topological insulator-based system. So, for example, quantum anomalous Hall effect, topological magneto-electrical effect, and image magnetic multiple. And so, in this term, we usually call axion electron dynamic term. So, if we want to realize the axion insulator in this kind of magnetic doped TS system, it should satisfy these three conditions. The first condition is the TF film needs to be in the 3D regime, and all the surface of this TF must be gapped, and the bulk of the TF needs to keep the time reversal symmetry. So, we know that we have realized the quantum anomalous Hall effect in the chromium doped and vanadium doped system, and these two systems has different TC. So we are thinking to fabricate this kind of quantum anomalous Hall sandwich structure. The bottom layer is 3 quintuple layer chromium doped bismuth antimer telluride. The top layer is vanadium doped bismuth antimer telluride, and the middle layer is 5 quintuple layer bismuth antimer telluride. So at very high, if the magnetization of the top layer and bottom layer parallel, we will realize the quantum anomalous Hall effect. There is the Chiral state. So because of different HC, so in some magnetic field regime, we can make the magnetization of the top layer and bottom layer anti-parallel aligned. So in this kind of situation, the top surface is gapped, the bottom surface also gapped, and there is no eddy state. So this kind of state usually called axion insulator. We find this kind of state satisfies these three conditions, so we can call it axion insulator state. So this is the TM image of our sample. We can clearly see this is 3 layer, this is 4 layer, and this is the 3 layer vanadium doped TM. So in this kind of anti-parallel alignment sample, we call it axion insulator sample, axion insulator state. So in order to confirm there is anti-parallel alignment in this kind of quantum anomalous sandwich structure, so we take the MF measurement and the in situ transport measurement. So we first, in this transport result, we indeed see the two-step magnetization transition. And we first apply the 1.5 Tesla in the sample and sweep the magnetic field back to the negative side. So at the minus 0.01 Tesla, we can see a uniform red color, means the top and bottom chromium layer and vanadium layer has the parallel magnetization. So when we further sweep the magnetic field to the negative side, we can see there is some green domain forms. And at about minus 0.09 Tesla, it shows the uniform green color. If we further increase the magnetic field, there is some blue color domain forms, and we can see the minus 1 Tesla, it shows uniform blue color. This means the downward parallel magnetization. So we can see at minus 0.01 Tesla, it indeed shows a state here, shows a uniform state here. This just means that the top vanadium layer and the bottom chromium layer has the anti-parallel magnetization alignment. So this kind of so when the magnetic field between these two HC, so there is this kind of anti-parallel alignment. This is just the necessary condition for the realization of the axion insulator state. So let's see the transport result. So this is the transport result of this kind of axion insulator sample. This is the Hall conductance. This is the magnetic field. So we can see at a very high magnetic field, they will parallel aligned. So this is just a quantum anomalous Hall state. This is E squared over H. So when you sweep the magnetic field back, because the chromium layer has a small HC, it first reverses the magnetization and forms this kind of anti-parallel alignment. If you further sweep to, when the magnetic field is about minus HC1, you will realize this kind of downward parallel alignment. This also become a quantum anomalous Hall state. So when the HC between the HC1 and HC2, there is this kind of anti-parallel alignment. So the top surface has E squared over 2H conductance. Bottom surface is minus E squared over 2H conductance. So the total conductance is 0. So this kind of state is called the axion insulator state. So this kind of axion insulator state is a good platform for the detection of this kind of topological magneto-electrical effect. So we know the magneto-electrical effect. So why we call it topological, just because in this kind of material, the magnetization and the electric polarization is parallel each other, and the coefficient between them is quantized. So we are, my group is still doing this, is still pursuing this direction. So let me show you the second work. So we fabricate this kind of, we also fabricate this kind of magnetic TI and magnetic TI heterostructure. But in this kind of structure, we use the same doping. We can see this is 3 quintuple layer bismuth antimaterite. This is 5 quintuple layer, 3 quintuple, all chromium doping. This looks like a symmetric sample, and we carefully tune the bismuth antimony in each layer to tune the chemical potential in each layer in the charge neutral point. So this means that we can achieve the quantum anomalous Hall state at 0 gate voltage. This is the transport result of our sample. We can see at 0 gate voltage at the base temperature, 30 millikelvin, it shows very good quantum anomalous Hall state. It's quantized and the longitudinal resistance is below 10 ohm. So, and the TC and when you increase the temperature, the Hall resistance shows this kind of hysteresis loop, and the magneto resistance shows this kind of butterfly structure. These are just the typical phenomena of the ferromagnetic material, and the TC of this material is about 19 Kelvin. So let me show you the gate dependent of this kind of sample. So when we tune the gate at the charge neutral point, almost 20 volts, we can see it shows very good quantum anomalous Hall state, and the longitudinal resistance is below 1 ohm. So this is the best quantum anomalous Hall state. So when you tune the gate, when you apply some minus gate voltage at minus 80 volts, we introduce some Hall carrier in the sample. There is a feature comes out. There is a hump shows in this kind of hysteresis loop. This hump feature is usually called the topological Hall effect. It corresponds to the chiral spin texture in the real material. So when you further increase this kind of minus gate voltage, this hump feature become pronounced. So if you apply the positive gate voltage, there is also a hump feature comes out. If you further increase the positive gate voltage, this hump feature will disappear. So in this state, this quantum anomalous Hall state corresponds to the barrier curvature in the momentum space. So when you give some electron, when you inject some electron in the sample, it shows this kind of topological Hall effect. It corresponds to the barrier curvature in the real space. So let's summarize the topological Hall effect as a function of the gate voltage. We can say that at this charge neutral point, the topological Hall resistance is 0. So this is just the quantum anomalous Hall regime. So when you inject some Hall carrier or electron carrier, there is topological Hall effect, and the maximum of the topological Hall effect shows when the chemical potential is crossing the Barkov valence band. and in the electron-doped regime, is the topological Hall resistance is lower than this side. So there is a asymmetric behavior in this electron p-doped and n-doped regime. So this is the magnetic field dependence of the topological Hall resistance in the sample as a function of the temperature. We can see this harmful feature will disappear with the increase in the temperature. So at 5 Kelvin is almost 0. We can see at when the gate voltage is minus 200 watts at 30 millikelvin, the topological Hall resistance is about 1.65 kilo. This is much higher than the previous system for the topological Hall resistance. And this kind of large topological Hall resistance just indicates the higher density of this kind of ferromagnetic texture or small size of ferromagnetic texture in this sample. And we know that in the so we want to explain why we can observe this kind of crossover between topological Hall effect and quantum anomalous Hall effect in this kind of magnetic TI semi-structure. So we know that in magnetic TI, the ground state is ferromagnetic. So there should be no stable spin texture. So, but we observed in our sample, this harmful feature is observed around the QAH field regime. So we suspect maybe there is some chiral domain wall in this kind of sample, and this kind of chiral domain wall can form the chirality in this kind of sample. So this is this is just a schematic for our sample. This is the blue color is spin down, the red color is spin up, and between this kind of spin up and spin down in this kind of magnetic domain regime, there is this kind of counted spin order. There is some chirality in this kind of regime. So when the magnetic field is tuned to the QAH field regime, it can show this kind of chirality in this kind of sample. So
the second image is that real image or that also schematic?
Also schematic. Also. Yeah. Yes. And in order so we want to explain this. You know, we usually know that this kind of chiral spin texture is proportional to the DM interaction in the sample. So Chaoxing at Penn State help us to do this kind of simulation. This is a simplified band structure of the magnetic TI. This is the conduction band, and this is the valence band. It all forms the quantum well states in this kind of thin film. This is the surface state. This is top surface. This bottom surface. So we calculate, because this kind of magnetic TI film with respect to the XY plane is breaks the mirror symmetry. So this kind of KXY, so KXY is 0. So we just consider the KYZ. So we calculated the KYZ of the quantum well state and surface state, just this kind of model. We can see for the quantum well state, it shows this kind of phenomena. It shows a peak when the chemical potential in the valence band. This is the surface state contributed the KX state. It shows a double peak and around this kind of magnetic exchange gap regime. If we add them together, we get this kind of phenomena. This phenomena is very similar to our experimental observation. Let me compare these two, the experimental data and the theoretical calculation. This is the theoretical calculation. This is our experimental data. It both shows this kind of asymmetric phenomena between the p-doped and n-doped regime. The reason is that we know that the magnetic exchange gap in this kind of magnetic TI film usually much closer to the bulk valence band. So the only difference between these two figures is in this kind of charge neutral point regime. We can say that in this one, it shows the quantum anomalous Hall regime. Although here we get this kind of GMA interaction is non-zero, but there is no topological Hall effect in our experiment. the reason is that in the quantum anomalous Hall regime, the bulk is insulated. There is no carrier to support the charge transport in the sample, so there is no harm observed in this kind of quantum anomalous Hall state. It's also reasonable. So now we come to the end with this summary. So we are the first to realize the quantum anomalous Hall state in the chromium-doped and vanadium-doped system. And you know, up to today, there are only these two systems with the quantum anomalous Hall state. And we are the first to realize the axion insulator state in this kind of quantum anomalous Hall heterostructure. The realization of the axion insulator state is good for the detection of the topological magnetoelectrical effect. And the second work I did in the Penn State is about this crossover between quantum anomalous Hall effect and topological effect. And the observation of this crossover quantum anomalous Hall effect and topological Hall effect will help us to understand the baricurature between momentum space and real space. So this is the collaborator. So most of this my student and collaborator Chao-Xing and Moses and Yijing. And the theory was done by the environment was done by the Landau at Rutgers University, and the theoretical calculation by the Jianong Dang from the New Hampshire University, and the realization of the quantum anomalous Hall system in the chromium-doped system. I did this experiment in Tsinghua University of China, and this is my supervisor Qi Kunxue. And the dilution measurement at that time was done in the Lili's group in the Institute of Physics. And at MIT, I realized the vanadium-doped quantum anomalous Hall system. And this work is supported by 2DCC and NSF, and also DOE and Army Research Office. Okay, thank you.
So while they queue up questions online, we might as well have questions in the room for a little bit.
Yeah.
On your first slide, you have your coffee mug turning into donut shape.
Yes.
Can you
I just want to see this the coffee cup and the donut has the same topology. Yes. Yes.
You were explaining about bismuth telluride and antimony telluride, chromium doped this thing, and how do you mix those? I mean, what doping?
Oh, that's you know we use the MBE to do this sample. We co-evaporate these four elements in the MBE chamber to get the film of the chromium doped bismuth and telluride film. Yes.
It is a follow-up for that question. So, do you know the bismuth and the other metal? Do they be segregated or they become an alloy?
Well, this is for the bismuth telluride film, they are usually 5 layer. It's tellurium, bismuth, and tellurium. So when you do some antimony inside, this kind of antimony only can substitute the bismuth size. So it will uniform doped in this kind of bismuth layer. There is no antimony layer in the tellurium layer. Yeah.
And when so basically they mix each other in
yes.
Do you have any evidence for the scanning?
No experimental evidence. That's because the reason is also this number, the topological resistance is too high. The ischemia size should be very low. I think should be at the limit of the definition of the ischemia, very small. So that's the reason we didn't claim there is ischemia in our system. That's based. Our system is a very good ferromagnetic system. There should be no ischemia.
Right.
The ischemia cannot be formed in this kind of ferromagnetic system.
Yeah, that's what I think.
Yeah, so that's we claim the Chiral domain wall.
Yeah. So this you call topological Hall effect. It does not necessarily come from the Chiral domain wall.
Yes.
It could be simply just due to the very curvature of the band, right? So when you tune it to the electrons doped side.
Yes.
The probably just at that side, the Berry curvature of the band is higher.
But you know that Berry curvature, I cannot agree with this because that if you said this correct, when you sweep the magnetic field upwards and downwards, it should be overlapped. But here, when you sweep the magnetic field upwards and downwards, it's not overlapped. That is definitely related to some magnetization property in the field. It's just because of the Berry curvature in momentum space.
Is there any effect of number of layers of these materials on the quantum anomalous Hall effect? And they qualified that question with one more comment. They said,
all over the world now there are just only about 5 groups can group this kind of quantum anomalous effect. Different groups using different thickness of the sample. And the regime I can give you is from this 4 quintuple to 15 quintuple, this kind of regime. Nobody can realize the quantum anomalous Hall effect with the thickness above 15 quintuple.
because they followed up with, could the same effect be seen with 2D material regimes?
Yes, if the 2D material with the quantum spin Hall effect or topological property, in principle, you can also realize quantum anomalous Hall effect. Quantum anomalous Hall can be considered. There are 2 channels in quantum spin Hall effect. If you can kill one channel by the ferromagnetic doping, in principle, you will realize the quantum anomalous Hall. For example, in the tungsten telluride, I just tell you, in monolayer tungsten telluride, there is the quantum spin Hall effect has been observed. So if you can introduce some ferromagnetic order in tungsten telluride, kills one channel, so in principle, that should be quantum anomalous Hall effects. Yeah.
So is there an explanation why the other usual suspects of elements that might give you magnetism does not?
Oh, actually, in my PD, I was trying all the transition metal first in this kind of the periodic table, and I just found 3 elements can get this kind of ferromagnetic property. One is the chromium, the other vanadium, and the third one is manganese. So the reason the first one I choose the chromium is just because theory said chromium is better. So in my PD I tried the chromium, and the theory also said the iron-doped TI also a best choice. But in our experiment we found iron-doped TI there is no hysteresis loop. So that's the reason we built up the iron-doped system. So the vanadium-doped system, the reason I was trying, as I mentioned, the ferromagnetic property is better. So I'm an experimentalist. I see this ferromagnetic property is good, so I want to try it. But so I just tried 20 sample with the calibration of the previous post-osmosis, and we just measured 20 sample. We finally get this one very good quantum anomalous state. So that's vanadium-doped system is much easier than the chromium-doped system. So some DFT calculation sometimes is not very accurate. Yes.
Yeah, because there could be multiple effects. There could be just thermodynamically that won't make sense, or it could be the fact that the oxidation state is wrong.
Yes.
So
I know that the theoretical paper, the authors very well. They published a science paper in 2010. They used the DFT to confirm this kind of magnetic doped GIA is quantum anomalous state. The reason there is no quantum anomalous state in vanadium doped sample that's because there is some impurity band. So later I talked to them. They told me in this kind of magnetic doped GIA, they usually impurity band. So at low temperature you can localize them. So it cannot affect this kind of the observation of the quantum anomalous effect. Yeah.
Okay, so I think we're going to close down. If anybody online wants to speak with Trezu directly, just raise your hand and we'll unmute you. But otherwise, we're going to close down the session for now. So thank you so much, Trezu.